Okay, how are we doing on the these first three?
Good.
I wasn't paying attention that it was deuterium.
Yeah, it's okay.
Any questions about those first three?
Can you go over? Yeah, can you go over the third one?
Third one is Gabriel synthesis. KOH deprotonates the imide, which is acidic enough to be deprotonated by that. Make the anion. Throw in this here, alkylating agent. Nitrogen does SN2. Just need an arrow. Kick off the bromine ion. We get the alkylated phthalimide, and then we hydrolyze. We hydrolyze the nitrogen carbonyl. Nitrogen carbonyl, we release the amine, and we make 2 carboxylic acids. The amine is going to be protonated because we're under acidic conditions, but I just showed it neutral. But it wouldn't be protonated. You'd have to work it up with base to deprotonate the amine to make it neutral. Gabriel synthesis of primary amines. Yep. Lactic acid would be the monomer that is polymerized to give polylactic acid, which is used in 3D printing. It's a thermoplastic, more liquidy with heat. How do you do on that one?
I got it.
Question?
Yeah.
Do you remember that it's a hydrolysis reaction, so water is reduced all the way?
No, I just added it.
What else would they might be? Yeah, I mean, this OH condenses with the carbonyl and you eliminate water, and then this oxygen is bonded here.
That's why. Okay. I thought it was this.
I mean, if you have an alcohol, I mean a carboxylic acid, and maybe an alcohol, these react to essentially give what? With loss of water. You would get the ethyl ester, because this adds here, you lose water, H2O. Now this oxygen is now bonded here. So you get the ester plus water. That's a Fischer esterification. Yes, it requires acid, but it's a condensation reaction. So something's going to react here, and you eliminate the OH plus the H from the nucleophile, well, that guy. If we draw this, just draw it like that, and let's say this OH from another molecule condensed here, the H is lost with that to make water, but what's connected to this? It's connected here, carbon with a methyl, and then here. So this is where one of the molecules condensed with the carboxylic acid. But then this one can condense with another, and so you get rid of the water, and you join the other oxygen, and it's bonded to that there. And then you get rid of this water, and you bond the other oxygen, and it is a methyl with a carboxylic acid. And someone please stop me. And then you go back and you say, well, what polymer did I just make? What's the repeating unit? Carbonyl OC methyl. Carbonyl OC methyl. You could show it like that. Carbonyl OC methyl repeating unit. That's shown a little bit different because you can also see another repeating unit. That is, start with the oxygen. That is OC methyl carbonyl. OC methyl carbonyl. OC methyl carbonyl. And so that's also a repeating unit that can be shown. But that right there is what we started with. Just turned around backwards. It's O carbonyl C methyl. O carbonyl C methyl. No, that's not it. Because this is OC methyl carbonyl. It's all up here, it's just how you want to show it. O carbonyl C methyl. O carbonyl C methyl. So right here. O-carbonyl C-methyl, O-carbonyl C-methyl. That's how it is. So they could be different repeating units, I mean, up there, depending on how you want to classify your single unit.
So for the right hydroxyl group, could that be any group?
Like what?
Like chlorine or?
Well, if it was a chlorine, when these reacted, what would you eliminate? HCl. When you say condensation, typically you're saying you're going to lose water. The chlorine actually, that's acceptable though. That would give it. And actually, that would be more chemically appropriate because the Cl is more activated for leaving and doing the chemistry. So that would get pretty much full credit. It's just recognize that when it happens, you're losing HCl there instead of losing water. Okay, any other questions about that one? How many got lactic acid there, or you didn't know the name of it, but got good? Okay, nitrile chemistry. Here. You can basically add H2S to a nitrile to get a thioamide. If that was oxygen, it'd be a regular amide. This is called a thioamide. They're pretty common. H2S typically requires a basic catalyst. When you have an acid catalyst, first thing you're going to do is protonate something. Same thing with a basic catalyst. If you have a basic catalyst, first thing you're going to do is deprotonate something. Well, you don't want to deprotonate this. I mean, there's no H that's lost, but you deprotonate this and it turns it into a better nucleophile. Now this will add to the nitrile, and then you're off. Get this? I was going to maybe show a resonance structure, but then I decided, no, I don't want to put another anion here. So instead I did a proton transfer. That is, move the H from here to that anion. That's a pretty strong base. You can take that. Then we can do resonance and make the pi bond to sulfur. Get this anion. Then this anion needs to pick up an H. Well, we can take it back from water to give the final product. And when you take an H from water, you regenerate hydroxide, which was the catalyst.
Is it necessary to use hydroxide in the reaction? Because could you do like 2 proton transfers instead and not?
Well, first off, whenever something is said to be catalyzed, that typically implies that it's not going to work well without the catalyst.
Okay.
Also, if it's in the mechanism, you should be using it.
But,
Otherwise, you just chose to ignore it. It's like, why did you ignore the catalyst?
but like if the NaOH like in a hypothetical problem wasn't there, could the reaction still?
This reaction does kind of work without the hydroxide, but since it's given, you should use it. I think the same mechanism is in the workbook without the catalyst. And then, yeah, you would need 2 proton transfers to get both the H's off the sulfur onto the nitrogen. Nitriles will react with H2S, but they won't react with H2O. Okay, H2S is a stronger nucleophile, right? The answer to that is yes. Indeed, it's strong enough that it will react with a nitrile. Sulfur is a great nucleophile. Still, though, a little basic catalyst here can help. How do we do on that?
Can the base attack first?
Yeah?
I didn't use the catalyst, so I started redoing it and ran out of time.
Well, if the catalyst is there, it's often very important, and you should probably use it very first move. Okay, this will be posted upstairs. A couple of summary tables that were not returned. Krenjal, may have didn't get to you in time. Tara, if you're here, please Jill. No name. Anybody got a blue printout with no name? Megan? Jack? Okay. You have a handout test 4 material. I sent you one by email yesterday. We'll split it up, one handout. Thank you for returning these at the end of class back down here. Any extras? Okay, test on Monday. Typical format, we have nomenclature of what? Acid derivatives, acids, esters. What else can we do? Amides? Yeah. Fatty acids, a little bit, omega, that type of thing. Similar format, a little multiple choice, predict the products, reagents, or something like that. Mechanisms, short answer. Questions about the test? And IR, any questions about IR? The spec will only be IR on test 3. Any questions about the IRs? There's a handout. Any questions about that handout? Yes. Page 52 in the workbook. Which two? The question was, how do you differentiate between these two here? Somebody tell us how we differentiate between these two. Well, this is what functional group? Ester, and this is what functional group? Anhydride. Were there examples of these in the handout? There was an anhydride, and there was something with an exclamation point. Two carbonyls. Two carbonyls. The anhydride is going to give two carbonyls. Clearly, you see it has two carbonyls, right? And the other one only has one. But you get two peaks. It's not so much because it's two carbonyls, but it's because of the two carbonyls can be both stretching like this, symmetrically. That gives one resonance or frequency. But they can also be stretching like this, and that gives a second frequency. So that's really why you get two carbonyls. It's called symmetrical stretch, asymmetric.
So if you have a symmetrical anhydride, you're still going to have the two carbonyls.
Even if you have a symmetrical anhydride, you get two. That's why a couple of y'all made the aldol product in lab, and it's got two cyano groups. It is symmetrical though. It's actually not entirely symmetrical, but it only gets one nitrile in the IR. That's just coincidence. It should theoretically get two. Anhydrides typically always gives two, and they're always clearly resolved. Because of that, is there a spectrum where you had narrowed it down to those two?
The one on the right.
Okay. Somebody labeled the carbonyl peaks for you. That's awfully nice. I wouldn't expect that. But it looks like there's only one carbonyl there. So which one is it? As long as everything else is right. Ester, don't forget your sp3CH, sp2CH, which the second compound on the top does have both. So hopefully this does show both. There's no triple bond stuff. There's no like OH or NHs. Okay. So yeah, you narrowed it down. It's just the anhydride's going to have two carbonyls. Was there an anhydride on this page? Looks like no. Was there an anhydride in any of those example problems? Was not? Good question. Any other questions about IR? Question?
It's not about IR, but it's about something else. So when you dehydrate amides, you get, or when you make turn to nitrile, you also make the acid. But then wouldn't the acid also react with the nitrile that you just formed to make the carboxylic acid?
No, tell me again. Dehydrate and primary amide.
Dehydration of,
Primary amide to a nitrile using what reagent? Acetic anhydride,
yes. And,
which
or
can be
salt.
done. Orthionyl chloride.
Yeah.
Okay.
And then that usually makes acid. As
Makes what acid?
either HCl if you use alcohol or if you use acetic
Okay,
acid.
so it makes ACl, yeah. So you're saying what?
So then wouldn't that acid interact with the nitrile that you just formed?
It's theoretically possible. I mean, you could protonate the nitrile. In practice, the ACl is usually driven out your condenser. You can actually hold pH paper above it as the reactions go in, and you'll see the gas, ACl coming out. Theoretically, but what would that lead to? Think about that. So in practice, it works out. It's a reasonable question, yeah. Yeah, your product could react with the reagents. But in practice, it doesn't. One of the reasons being the ACl is driven out. It's good thinking, but it's a very good reaction. Other questions? A few miscellaneous things. I think the anesthetics for dentistry, that's kind of hopefully interesting to you, and it's very relevant to basic organic chemistry, which is what we're covering here. How do we do on those? The four in the middle, the question was, rank the following from shortest acting to longest acting. Which would be the longest acting of the four? Anybody get that? Which would be the longest acting? Anybody get that?
The most
Anybody? Let me rephrase. I'm not asking if you got it right. I'm asking if you made a choice. Anybody make a choice of which one?
First one.
Which one?
First one.
The first one would be longest acting. Okay, why did you choose the first one?
Longer is causing more hysterical.
I can't hear you.
The bottom one.
Causing more steric hindrance, because,
More steric hindrance?
yeah.
The first one, does it have more steric hindrance?
The fourth one.
But it's,
Let's see. I don't think it has the most steric hindrance. Why are you saying it has the most?
well, I looked at the two chains, like the CH2, CH3, and
Well, compared to this one, I agree it's got more sterics than this one because, I mean, that's just one carbon larger. That's not much of a difference. It's out there. It's a disubstituted nitrogen. The difference is this one has an ethyl on the carbon next to the carbonyl. So the ethyl next to the carbonyl is significant more. Yeah, that's more sterically hindered than this one. But what about these over here?
The bottom one.
Yeah, still have.
Because this has a group on the carbon next door, and then the nitrogen has that. I don't know. I was thinking that this did not have an H here, so this is disubstituted. Also disubstituted there. Well, let's look at these. Which one's more sterically hindered over here, top or bottom? Bottom, because see, this floppy thing can kind of move over here. And if a nucleophile wanted to approach the carbonyl, if this thing had bent over here, it's like, I can't approach. But this is not as big, and so it can get through there. I think the question boils down to these two. These two look the most. I don't know if there's an exact answer here. The exercise was to think about it and to give a ranking. I mean, maybe it's hard to distinguish. I think these two are the most sterically hindered. Now, what you can do is you can look these up and you can get what, like a half-life and the recommended time that dentists look at. Say, if I want my patient to be numb for 3 hours, which one should I give? Well, not Novocaine, but Novocaine is going to last for 3 hours. Because Novocaine's at the bottom. What type of derivative is it? What type of acid derivative is it? These all get metabolized by hydrolyzing the amide. What's that? Ester. Is ester going to be hydrolyzed faster? Yes, it's more reactive. Yeah, this is hydrolyzed relatively quickly. Novocaine is a short-acting anesthetic, like if you want to be numb for 10 minutes. If you want to be numb for 3 hours, then I'm going to give you Novocaine because I have to give it to you every 10 minutes, and you're going to get tired of the needle. So they're going to give you something more like bupivacaine. I don't know how to pronounce it, but the bu probably comes from the butyl group. By the way, these methyls up here sort of also protect the carbonyl. They look like they're kind of away from it. But still, if a nucleophile is swimming around, and it's like, I'm heading for the carbonyl, I got to... So the methyls do kind of sterically hinder a little bit. And that's why they were originally put there, because they wanted to sort of slow the metabolism down and make them longer acting. This guy over here, this was a very good question. This could have been asked in Organic 1 during week 2. Anybody look at this one?
What's the question?
Is it a, what's the question? Is it an electronic effect or steric effect? Anybody get that one? Any last, any questions about any of the miscellaneous things there? Neurogases, synthesis of Zyvox. Hopefully you look at these things. This is chemistry in action, hopefully to make it relevant and the importance of what we're looking at here. We did the first one in class, I believe, on Wednesday, yeah?
Yeah.
How about this one here? I mean, you can put a methyl there on that end too. I just sometimes write the methyl in on the ring. Alcohol. By the way, I do want to look at one more thing in here. It's the, I think it's in this current handout. Yeah, we want to look at the NADH, that type of thing. It's very important in biochemistry. So, hydride adds, electrons up. Where does that H come from? What type of aqueous workup? Or it could come from solvents. The sodium borohydride, that H could come from solvents, like ethanol. Okay, this one down here, let's see. That tertiary alcohol with the 2 ethyl groups on there. Now, yes, this does require 2 equivalents. It may not say that, but with Grignards, you just keep adding. It's going to add twice. That's the typical product. Now, hold on. I mean, that's the product that I want you to show. But what if you were taking some type of exam or something, I don't know, one, and and there's multiple choice, and that answer is there, and then the other three are like garbage answers.
I'm going.
For that.
Is that a reasonable answer there?
Yeah.
How do you get to that product?
You have another thing.
Grignard adds up, down, kick off chlorine. There you go. Then you're like, well, I thought it would add twice. Yeah, but whoever made the test out apparently didn't. And this is that. The other three are clearly junk because it's like mechanistically, how would the other three happen? Nobody knows it. They're just. And so, in the context of the question, you go with that answer. But for us, I'm telling you that with Grignards, you're going to add twice, or with hydride reagents, unless it's Dibol H. Dibol H only adds once, and cuprates only add once. Question?
If you're to ask us for the reagent and we put a Grignard, would we have to say 2 equivalent or just assume that it adds twice?
I'd probably let you just say, because I didn't say 2 equivalents here. Grignards are added twice. I would expect you to understand that it requires 2 equivalents. But necessarily showing it, I probably wouldn't, because I'm not showing it like that. Oh, we have a cuprate down here. Oh, that sounds like it's going to only have once. What are we starting with?
Start with say
Acid chlorine. Well, that's the product I just erased. That's the ketone product.
with the
Ethyl. Because it only adds once. Great way to make a ketone. So those are a mixture of simple additions, which that's just only a simple addition. This involves an addition elimination followed by a simple addition. And this is an addition elimination. Aldehydes and ketones don't have that leaving group, unless it's something very unique going on. Aldehydes and ketones will be our topic, our main topic, test 4. We did a little bit here. It's an interesting reaction here. Synthesis of Zyvox, which is a fairly new type of antibiotic. Anytime there's handwritten, this is chemistry we've seen. We pick up here, this is a mesylate, like a tosylate. Azide can displace the mesylate, SN2. The azide can be reduced to the primary amine. We kind of looked at that in organic 1. We didn't spend much time on it mechanistically, but the primary amine can then be reacted with acetic anhydride to make the acetamide. A number of you made acetamides in lab, right? And the acetamide is the final product. Zyvox is an acetamide. It's also got this carbonic acid sort of derivative here. Back up there, they get the amine on here by an NAS reaction, displacing the fluorine. Which fluorine is activated for displacement? The one paired to the nitro group, right? I mean, a lot of good chemistry is there. Look at this reaction here, though. At this point, they react this amine with this. It's kind of a carbonic acid derivative. Does it make sense that they get this product? Add your carbonyl electrons up, back down. Which one do they kick off? Chlorine, the better leaving group. So it displaced the fluorine.
That's a nice, beautiful acyl substitution.
Yeah, it's a beautiful acyl substitution. They got a little epoxide chemistry in here. This is actually an interesting reaction because what's reacting with the epoxide?
I guess the
Inbutyl lithium is removing this H and they're making an anion here. That anion reacts with the epoxide. Where's it going to attack, left or right? SN2, always least sterically hindered. Yeah, electrons off. That should give an alcohol, but how do you get this product? What's going on there? What's going on there is the alcohol, after it opens up, is coming back, attacking the carbonyl and kicking off that oxygen. If you look at it, what's going on there? It's a very interesting outcome. If you look at it, you should be able to follow it through. In the end, you start with a very basic starting material, which you can buy, which how we got in the lab upstairs, and through synthesis, you make Zyvox, and now you're making billions of dollars. Well, that's a lot of money. It shouldn't be billions, it should be millions, but very expensive, and there you go. That's the power of chemistry, and it's curing disease and making money along the way. Question?
For the cucurate, could we use a methyl instead of an ethyl in that, like methyl 2-CuLi? Is that possible or no?
No, yeah, you can have any R group. I mean, methyl 2, Cu, lithium.
Okay.
Yeah, I mean, this can vary from any R group. Methyl, alkyl, propyl, you name it. Yeah. One other thing, and then I want to introduce some of the test form material as we can. The current handout. Yeah.
All that oxidation production.
We looked at the redox cycle there. Very important. Redox cycle going from carbonyl, aldehydes, ketones to the alcohol. Okay, illustrates very important redox cycle. Now, in terms of reducing, in class we introduced hydride reagents, and you use sodium borohydride in lab. It's very convenient solid. Easily weighed out. Your body doesn't use these. Your body uses something like NADH as a hydride source. Okay? That is described over here. The name, etc. But right here is NADH. How does it supply hydride? What happens is, this ring here, these electrons move here, these move here, and then it shoots off the H and the two electrons, almost like a leaving group. I mean, it's a leaving group from sodium borohydride, but it's a very unique. What favors this to push this off? Well, look at the ring. What does the ring become when it shoots off the hydride? It becomes aromatic. Now, it does have a positive charge, but that's the driving force. Hey, get hydride, you go, so I can become aromatic. But it's a positive charge, so going back that way, the charge is relieved. So you can get sort of the reverse, where the hydride comes back in, you go back and you relieve the charge. So it's a back and forth. Both sides are sort of have some favorability, and this is an equilibrium, and this is, so it can exist in both ways. But when it's like this, it's a hydride source in your body. And of course, coming this way is an oxidation, because over here you lose an H. And if you lose H, that's an oxidation, right? And if you gain H, that's a reduction, right? We've already said that. And so in biochem, you'll likely see things like, good afternoon, class. Today we'll be looking at the reduction of what? Pyruvate to lactate using NADH, and there'll be an expectation that you know what's going on here. Yeah, hydride source. What's going on here? The ketone is being reduced to the alcohol. There's a new H here. Boom, electrons to the O, pick up an H. At the same time, the NADH gets oxidized to NAD+, because it's coming here. Et cetera, et cetera. And then if you want to design a drug, for example, to lower cholesterol, something like Lipitor, it targets an enzyme. It targets HNG-CoA reductase. Lipitor does. What does this enzyme do? Well, that enzyme has NADPH associated with it. it reduces HMG-CoA to that guy there on the way to cholesterol. And so if you can inhibit this enzyme, you don't make as much cholesterol. What's going on here, if you look at it, H minus, in, up, down, kick off the sulfur. Well, that would give an aldehyde, right? But guess what? Another H minus comes in, and we get two H's there. That just picks up an H, and you get the CH2OH right there on the end. Just like you mechanistically you should. So this is the, because it adds twice, right? Aldehydes. So there you go. There's your end product on the end. That's called mevalonate. You keep going, you'll get cholesterol. But if the drug stops this from happening by inhibiting the enzyme, you don't get as much cholesterol. So what we're doing is looking at basic ideas to help us then understand larger ideas. Okay. Let's see if we can introduce a little bit on the yellow page. Is that the one from today?
Yeah.
I sent you one by email for next Wednesday. This is an overview of a lot of the aldehyde ketone chemistry we'll be looking at.
Oh, it's 2S.
We have an aldehyde or ketone. They're both going to be the same to us. They both react to give similar products. Aldehydes do tend to be a little bit more reactive. Hopefully you can be able to give an argument for why. But both can give any of these products. What type of reactions will we be doing? Well, they're all shown here. Please look at them. You add water and you get a hydrate. Oh, hydrate because you just added water. But structurally, it's also known as a gymdiol. It's a diol. What does gyminal mean? Twins, sort of there, okay, as opposed to vicinal. A cyanohydrin, react with ACN. Cyanohydrins are very important. They're very toxic because they release HCN. That is, they can reverse and give off the HCN. We'll make things like acetals. What are these guys called down here? Oban-N? Amines. Amines, also known as what? Schiff bases. We'll make enamine. Enamine, everybody know enamine, right? Yeah. What's it? It's like a rapper, but
Oh, Lord.
what's his name? Enamine?
Eminem.
Oh, okay. I can't keep up with it. Enamine. Oh, look at this. What is this? What is this?
That's Wolf Kishner.
Wolff-Kishner. We said we'd look at it during test 4. Wolff-Kishner reduction? Yeah. We can also make alkenes. Alkenes. That would be a name reaction, a Wittig reaction, one of the top 10 reactions of organic chemistry. There's 20 or 30 top 10 reactions. Okay, that's a large summary, okay? And on Wednesday, we'll start probably right here. Going around it, starting at 12 o'clock. Last questions. Questions about lab.